Our focus today is the conversion of logarithm to exponential notation. And so how do we understand this one? So again, we always understand that one by making an elaboration. Okay, by making an elaboration. So notice that if we have this notation, our notation is log. Okay, we have in here log of x with a base of a, which is equal to y. Now in its exponential notation, that is the same as saying a, okay, a raised to y, okay, raised to y is equal to x. So when we are going to convert our base in the logarithm, okay, which is a, that is also our base in the exponential notation. So again, our base in the logarithm will be our base in the exponential function. And of course, our result in the logarithm, which is y, will be actually the exponent in your exponential notation. It will be the exponent. Okay, it will be the exponent. So this one is actually the a is actually the, what is that? It is the base. Okay, and of course the other one we have in here, oops, I'm sorry, here, okay, that is actually our exponent. So that is actually our exponent. So this is the technique of converting logarithmic notation to exponential notation, okay, or exponential notation to logarithmic notation. Now there are laws that we need to consider in the logarithm, okay, but before that we have laws. We have the laws of logarithm. So we have in here, what are the laws of logarithm? What are the laws of logarithm? We have in here the first one. Okay, the first one is actually log of a, or log of the product of AB to the base E is equal to, that is the same as log of A with the base A plus log of B to the base A. Now, notice that before we continue this notation, your A, okay, your A, the base A, okay, we have to consider that our base A should not be equal to 1. And of course, our A must be greater than 0. And B must be also greater than 0. Okay, so that when these things are when A is not equal to 1 and your A is greater than 0, your B is greater than 0, then for the logarithm of the product of AB with the base A, that is the same as you add the individual logarithm. So log of A to the base A plus log of B to the base A. So that is actually the product of the logarithm. Now another one in here is log of the quotient of a over b with the base a and quotient. Now, so that if this is a product, its corresponding converted simplified form is in the summation, this must be in the subtraction, okay? By saying log of a with a base a is the same as minus log of b with the base a, okay? So we subtract, okay? We subtract. Now, what about the other one? The power of logarithm, okay? The power of logarithm, which is presented by this one, log of a raised to c with a base a, okay? What must be its simplified form? Now, before we show the simplified form of this one, we have to consider that your c in here must be any real numbers, okay? So that is the value of your c. What about your b? Must be greater than 0. Your a must be greater than 0. The base a in here, it must not be equal to 1, okay? So now let's try to see the power of logarithm. How do we simplify this one? Now if we have this one, that is the base will be converted as a factor that is the same as saying c times log of a with the base a. So that is the converted or simplified form of the following logarithm. Okay, the product of logarithm, the quotient of logarithm, the power of logarithm. So in the product, we add. In the quotient, we subtract. If that is in the power, we get this power as one factor, okay, multiplier, okay? So that is how to deal with the laws of logarithm. There are so many laws of logarithm, but of course, this is only the one that I will introduce for our next lesson, okay? For our next lesson. Another one, we have what we call in logarithm change of base, okay? Change of base. So that in the change of base, we are given the notation log of x with the base b. Now, how is this? When we say log of x with the base b, now we can convert that one by saying log of x with the base a over log of b with the base a. So meaning to say, we can convert this one into quotient form. So if we convert this log of x with a base b into a quotient form, we have to see to it that the individual base in the quotient form must be the same, okay? Must be the same. Okay, so that is the change of base. Or if we are going to have the other way of writing it, if we have log of x with the base a over log of b with the base a, notice that they have the same base. The logarithm has the same base. And so that if they have the same base, we can also write this one into its equivalent form. That is the same as saying log of x to the base b. Okay? So that is the meaning of the change of base. Okay? Change of base in logarithm. Another one in here is the natural logarithm. Okay? Natural logarithm. What do we mean by that? When we say natural logarithm, it is actually a logarithm. Okay? Logarithm with what? With base e. What is e? It is actually the Euler's number. Euler's number, or it is called to be natural logarithm or natural logarithm. Okay, with logarithm with base e, or the natural logarithm. Okay, that is of course, okay, denoted by what? Okay, denoted by ln. Okay, denoted by ln. Okay, so that is the natural logarithm. So that if we say natural logarithm, this one, okay, natural logarithm x, the logarithmic form of this one is log of x with the base e. Okay, with the base e. So that is the meaning. Okay. Now, so that if we are going to consider also the exponential form of this one, exponential form of this natural logarithm x, which is equal to y, this is the same as what is the base e. And what must be the exponent? The exponent must be y, which is equal to x. Yan. So that is the conversion. Okay, that is the conversion. Okay, we have to remember also that when we have a natural logarithm of 1, the result is always 0. The result will always be 0. Okay? Another one, the natural logarithm of e, the result will always be 1. And of course, the natural logarithm of e raised to the x power, that is the same as the result will be x. And if we have in here natural logarithm raised to the power L, natural logarithm x, the result will be x. Okay, so these are the things that at least we will be encountering when we move on with the limits of the exponential function. Okay, the limit of the exponential function. Okay, so you have to remember them. Okay, remember them. To consider the limit of the exponential function, we have to remember the following theorem that I will be writing it down. Okay, for theorem number 1 of the limit of the exponential function, it says in here for any real number, okay, for any real number a, we have a limit, okay, we have the limit of e raised to x as your x is approaching a. The result of this one will always be e raised to a. So again, the limit of the e, which is the natural number raised to x, as your x is approaching a, the result will be e raised to a. Now, notice that is actually direct substitution, okay? And we have another statement saying, if b is greater than 0, and of course your b is not equal to 1, then we can have also a result of, or then we can have a limit that states that the limit of b raised to x, as your x is approaching your a, the result of this one will be b raised to a. Now, it says in here, if b is greater than 0, that is actually the b in the base, okay? Greater than 0, but not equal to 1, then if we have the limit b raised to x, as your x is approaching a, the result will be b raised to a. Again, notice that in this theorem, it is actually a direct substitution, okay? It is actually a direct substitution. Now we have another theorem, okay? Let's say theorem number 2. Now what is the theorem, okay? What is the theorem? If your b is greater than 0, and of course your b again in here is not equal to 1, then we have a limit. Then we have a limit that states that the limit of the quotient b raised to x minus 1 over x, as your x is approaching 0, then the result will be the natural number b. So that is the result, okay? That is the result. Now, how do we apply these things, okay? How do we apply them? So that we can understand the application if we are going to give an example, okay? So an example in here is, it says in here, we have the limit of the quotient 5 raised to x minus 1 over 2 raised to x minus 1, as your x is approaching 0. Now, how do you use the theorem and simplify this one? Notice that when we are going to use the theorem, this form is actually somewhat like a formula. And if this is a formula, we will follow it in toto, okay? We are going to follow this one in toto. Now, remember, our b in here is always the base. Our x is the exponent. Okay, so that, notice in the theorem number 2, when we are going to directly substitute this one, the result will be indeterminate actually, okay? So, assuming na we do not have the natural number b, we will be having the direct substitution, okay? Okay, direct substitution of this one. So that is the same as 0, okay? 0, so b raised to 0, okay? Minus 1 over 0. So any number raised to b, any number raised to 0 is the same as 1 minus 1 over 0, the result is 0 over 0, and that is indeterminate. And so we do not make use of the direct substitution. Okay, so that we have this theorem to say that if we have this form of the exponential number, the result will always be in a natural number b. Okay, natural number b. So let's try to consider this one. Okay, meaning when we are going to elaborate this one, or when we are going to simplify this one, we have to see to it that the limit of 5 raised to x minus 1 over 2 raised to x minus 1 as your x is approaching 0 must be the same. It will follow this form. Okay, it will follow that form. So we will be following this form. Okay, and so how are we going to follow that form? Definitely we have to rewrite. Okay, let's try to have, we'll follow that form. So the limit of the quotient 5 raised to x minus 1 over 2 raised to x minus 1 as your x is approaching 0. Now we have to think of our multiplier that it will not change the problem. So what is our multiplier in here? Our multiplier in here will always be the magic one, or 1. Okay, but that 1 must be defined. Okay, so 1 is defined by x over x. So x over x is the same as 1. Now notice that we have this one as our multiplier. With that, we can now follow this form. Okay, we can now follow this form. We can create this form. So what is that? Notice that we can have the statement again saying the limit of the quotient, okay, of the quotient 5 raised to x minus 1 over x multiplied by x over 2 raised to x minus 1 as your x is approaching 0. Okay, as your x is approaching 0, what did we do? We just try to change the position, because so they are in the product form. It will never change the value in here if we are going to exchange the place of x and 2 raised to x minus 1. Why? Because they are in the product form. Okay, again, multiplying the limit of the quotient 5 raised to x minus 1 over 2 raised to x minus 1 as your x is approaching 0 with x over x will never change the problem. Why? We are actually saying that this x over x is the same as 1. Okay, it is the same as 1, so that if we are going to multiply 1 in here, this 1 will never be changed. Okay, so that is shall we say the meaning of 1, or the use of 1. Now notice that in the properties of the limit, we try to rewrite this one in here. Okay, so that is the same as, that can be written as what? It can be written as the limit of 5 raised to x minus 1 over, okay, over x as your x is approaching 0, can also be said that the limit multiplied with the limit of the quotient x over x raised to 2 minus 1 as your x is approaching 0. Notice that this form is actually the same as with this form. Okay, so it is the same. Now it says in here the result is the limit of the base or the natural number b, which is the same as this one. So what is the result of that one? It will give you that is the natural number 5. Okay, the natural number 5. Okay, so that is the limit of the quotient 5 raised to x minus 1 over x as your x is approaching 0. Now, what about this one? The same. It has the same with this one. It is just in the quotient form as if it is in the reciprocal form, this form. Okay, so x over 2 raised to x minus 1 is the same as this one in the reciprocal form. So what is that also? That is the same as the natural logarithm or 1 over the natural number 2. Yeah. So what would be now the result? What would be now the result? The result would be ln 5 over ln 2. Or that is the same as log of 5 with the base e over log of 2 with the base e over 2 log with the base e. Using the change base rule, that is the same as log of 5 with base 2. Okay, using the meaning of change of base rule. Okay, so that is how to apply the change of base rule and the theorem number 2 of the limit of exponential function. Okay, I hope you understand the use of this theorem. Okay, we can see more example in the next posted video.